Okay, so how is everyone today? Good, I hope. Any questions about how the semester's going or anything like that? Okay. Yeah?
I feel like I'm not being as successful with the substitution quite yet.
Okay.
So I was hoping to make the study group online.
I'm sorry?
I'm hoping to make the study group that's online tomorrow.
Okay.
For the class to see if things might cover it as a topic. And then teach it. Do you agree with that or disagree?
I teach it what?
Teach a little differently. No.
Yeah, of course. Yeah,
Yeah,
everybody.
but I mean, everyone has their own. But I mean, do you agree that that might be a good course of action?
Yeah. Yeah, I mean, definitely. You should find as many different points of view as possible.
Okay.
Yeah. I mean, you know, as long as it's like, I mean, here's the thing is that generally speaking, you know, folks like the math lab folks, they generally do a good job.
Okay.
But you know, if some you know, I can't warranty what they tell you. Is in the end what I mean.
Right.
And so, like, to be clear, instead of speaking in generalities, today's the 7th, right? Yeah. So, like, here's an example. Here, I'll give you an example of something I've witnessed. Some student has told me, "Oh, but my tutor told me that this was okay," not calling out the math lab in particular or anyone in particular. So if I give you an exercise like this, if I say something like, let the derivative of f be, you know, like 4x minus 3, and let the original function evaluated at 3 be equal to, you know, I don't know, 27. So we've done exercises just like this on numerous occasions. Here is a mistake. You know, so the instruction is find the original function f. So I see students write the following. So they write something like that. Now that's wrong. Why is that wrong? Because the dx isn't there. It's just that simple. So is it true that if I give you the derivative, then you can recover the original function by anti-differentiating the derivative? Yeah, that's true. That's true. But leaving off the dx is just not permissible. But all the time, in fact, I don't, you know, I would go so far to say that I'd be surprised that if someone this summer doesn't complain when they get points taken off for leaving off the dx. And then they tell me something like, my tutor or my engineering dad or whatever said it was okay. So besides things like that, yeah, by all means, go talk to the math lab folks. But like writing something like this is slang, like math slang. You know, just like you can, just like I'm sure that I am not speaking English entirely correctly at this time.
I heard if you work 8 to 5, when is the math tutoring open? Is it like an 8 to 5 thing?
I don't know. They told me that they sent you a message. Did they?
I'll take a look. If you work 8 to 5 and you're tutoring and you're in class, you know, the times it is extended open, what would you suggest then if you wanted to get extra help?
Yeah, that's not super convenient.
I think they have online.
Have online stuff where you can email it?
For the study groups, like right now,
Yeah. Another option, I'll try and remember to do this, is that, you know, this is not the first time I've taught this course. But I still have had the habit of like posting all the keys and all that. So then I can just send you all the link of, the last like 2 years that I did this. All the keys for all the assignments. Not for these, right? I just make it
Right.
up, right?
Hey, read it, yeah, that would be awesome.
Yeah.
That way we can
Yeah.
Yeah, that gives you some other things to do. I might even, because the way exercises go is I just sit down and I just say, yeah, I'm going to make that exercise. I don't look at any books or anything. And I just sort of just make it up.
Wait, will they have the steps to these? Or just the question?
It'll be just like it'll be like what am I trying to say? It'll be like the Twilight Zone, right? Like if you were looking at the last summer stuff, you probably wouldn't be able to tell the difference. Like, wait a minute, it looks exactly the same.
But if you show, like how you got to, you show the steps to it, or is it just the answers? When you post, what you're talking about, will it show?
I'm talking about like
Just the blank.
no. I'm talking about the keys, like
Oh,
videos,
so the keys, we'll have the steps.
videos.
You show your work, basically, is what they're asking.
Yeah,
Yeah.
you show the steps on how you get to the solution.
Have y'all seen the keys that I posted
Yes.
last night?
Yes. Oh, what-
2 semesters worth of those.
Okay, cool.
That's what I'm
Because
saying.
That would be huge. help. Because then we could do it on our own.
Right.
Yeah, and we could get more practice.
I
Yeah.
just need to see the problem worked out with different numbers, and then I can.
Okay, well, yeah, so then two semesters of that. If y'all would, if one of y'all, I mean, I'll try to remember it. I'm not very good at remembering. But let me write it down in my hand. And if one of y'all will just like email me and remind me, then,
Because
then,
because the math lab is not usually, like I try to go back and look at that today, and when I was able to, and it wasn't that much.
Use for the Lexus.
Yeah,
yeah. Okay, well, okay.
and that way we can see how you teach it, so it kind of goes hand in hand with what are in our notes, so it makes it a lot easier.
Right. So, I mean, okay, there's a couple things here. So, and we're kind of like, I kind of have the impression that we're kind of like dancing around them and trying not to say it. So I'm just going to say it, and you can nod assent or say no, well, whatever. So in the first place, there's some differences between instructors, right? That are just like, just because people are different. There's nothing like mysterious about that. And then there's also like different teaching strategies. So one strategy that is quite common, sad to say, and I'm not naming names, but just sad to say, one way to teach calculus is just to like lowball it, like only give easy questions and stuff like that. And that's not me. That's not who I am. That's not what I do. So usually when I teach a calculus course, very often, like the only one that I teach these days is like this one, because I taught this one last summer too. And all, the students say that, oh, this was nothing like calculus 1. Okay. Guilty as charged. Fine. But I chalk that up to me taking a different strategy. And that is that, so I'll just throw something out there that you might agree or not agree to. So here's the statement. The questions that we're doing in Calculus Math 1326 are a little bit more adventurous and exciting and possibly difficult than Calculus 1. You might agree to that to some extent. Probably. Well, I do that on purpose because I want to set exercises for you that are just slightly beyond what you're comfortable with. Because it's only in that circumstance where you can grow, right? I mean, you could grow a little bit if I just spoon-fed you an easy exercise. Easy exercise after easy exercise. But I don't think that's really that great of a teaching strategy. I don't think you're going to end up knowing very much than just like a recipe, a cookbook full of just, when I see this kind of exercise, I perform that kind of action. I don't think that's useful. Especially in a very high concept course like calculus. As a result, I take a different strategy. I give you some cookbook questions, some of them are, but some of them are kind of high concept. And those are the ones that more or less I'm hearing from you all that are difficult. Okay, guilty as charged. I'll be responsible for that. But and it would be unfair if I just poured that on you, you know, like for a variety of reasons. In the first place, I admit that they're difficult questions, and in the second place, that wasn't what you did in Calculus 1. So I think it would be unfair if the story ended there. But the story doesn't end there, because, for example, exercise 002, many of y'all found difficult. Okay. And news, that one is going to be graded out of 10. So that also means that you know, the key for 002 is posted, so you can see exactly how to come to the answer. And if it is the case that you didn't do so well on 002, then when the midterm comes and you come to the redo section, you can do the redo version of 002 and knock it out. It's not going to be the same question, but it's going to be the same concept. And if it really is the case that you understand the concept, then you'll be able to do that exercise. Yeah?
Will the midterm extra credit portion have every single X on it for everyone? And you just pick and choose which one you do?
So, to be clear, there's two kinds of ways to accumulate points in the course. One of them is the online homework thing, the MyMathLab thing. And what it is the way that works is that depending on how many and which questions I select, different of those assignments are worth different amounts. So like it might be the case that like 03 is like worth 23 points and 02 is worth 17 points, whatever. So I just add all those up and then and divide by the possible amount and get a percentage. That's your online homework grade. As for the WEX, all of these, so like we're turning in 5 things today. You just turned in these 4, and we're going to do a 5th one at the end. After this is over, I'm going to select 2 of them to be graded out of 10. The rest will be graded out of 1. So that means that today, 23 WEX points were available.
Out of curiosity,
yeah?
do you always choose the quiz?
No.
As one? Oh, so you don't always, okay. I just wanted to check.
So the question was, do I always choose the quiz? And the answer is no. I often do. One reason is just simply that it's really the only one that I can verify that you did, right? Because you know, what happens out of the classroom, you know, is anything whatsoever, right? Money goes a long way. If you take my drift.
We don't know that you have to. We've heard.
I'm just saying, okay? But so I can verify that you know that you did that one. So usually I select that one. So today there's 23 quiz WEX points available. Fine. So yeah, by the time we come to the midterm, it will be the case that there's been like 30 or so WEXs that are graded out of 10. I don't know what number it's going to be, maybe 30. Every one of those is going to be available for redo.
So all the ones that were graded out of 10 will be available for redo, but the ones that were at 1 point, we won't do.
You don't get to redo.
But those are just 1 point, so it's not a big
Right.
deal.
So what that means is that the out of 10 WEXs, you know, it's anybody's guess which one of these are out of 10. Even I don't know, right? Because I haven't decided. And I just like, you know, I'll go back to my office and just, you know, and I'll just do it. So you don't know in advance, but by the time of the midterm, that's your second hit, right? Your second, you know, whatever. And
we'll know, obviously, which
yeah.
ones were graded out of 10.
Yeah.
So we'll know which ones to study for.
Right, exactly.
Whatever we take.
And you should think in advance, like, you know, it might be the case that, you know, on, say, WEX 073, that was graded out of 10, maybe, and then you say, oh yeah, I could definitely do that one. So you should put, you know, I didn't do well on it the first time, but I could definitely do it good on the midterm. You know, put that one high on the list, like I'm definitely going to do that one. But, you know, maybe 052 is also graded out of 10, and you think, no, I didn't do good the first time, I'm not going to do good on the midterm. Forget it, that's a lost cause. Okay, then, you know, you should have a prioritized list of, yes, this one, not that one. You know? Because you might get to the midterm and decide, you know, I wanted to redo that one, but actually, no, I'm not gonna do it. Because, you know, if there's like 30 out of 10 Wexes, you'll have the opportunity to redo like 10, or, you know, somewhere like that, 10 or 12. Not all of them. So you're gonna have to make choices. So, you know, from a teaching point of view, there's at least 2 good reasons to do that. One good reason is that, you know, I'm a little concerned if you don't understand the concept when I ask. That's concerning. But in the end, all I need to confirm or deny is whether or not you understand the concept by the time you leave the course. So if you didn't get it in the 4th week, but you demonstrate that you do have it in the 8th week, so be it. That's fine by me. But the sword cuts both ways, which is that if you redo something, if you attempt a redo on the midterm, then that will be your grade, even if it is not as good. Because I just have to go with whatever the most recent measurement of that skill is.
I wanted to ask like a cookbook analogy, because when you talked about the spoon-fed question and the difficult question, I just want to understand what you mean by what you classify as a difficult question. Do you mean that like you've given us some of the parts, but not all of the parts, to be able to give the answer to that difficult question?
Okay, so I don't. I did say difficult, but that's not my word. What I said is that that's y'all's word. My word, my word for it is a conceptual question. So, like, you know, I call it a conceptual question, and then I hear y'all refer to it as a difficult question. So that's not my characterization.
My vocabulary is very low. Explain the conceptual.
So all I mean is like, you know, if I talk about, it's the difference between me writing a function and saying compute the derivative. That's a cookbook question. You've just got to know just like some sort of simple-minded, you know, like mechanical things. But if I say something about, you know, slopes of tangent lines and other things where there's concept involved, then you have to actually know that the relationship between derivative and slope and geometry, that the derivative at a point represents the slope of the tangent line of the graph of the function at that point. You couldn't possibly answer the question without knowing the concept. That's what I mean.
Right.
So that requires 2 things. It requires knowing how to interpret something and then being able to do that otherwise completely mechanical thing. So all I'm saying is that I give you some questions that are mechanical, cookbook, but I also give you some questions where you have to understand the underlying concept of what this really means so that you can know where to start performing your otherwise mechanical action. That's all I mean.
Okay. I guess my trying to figure out is like in class, you know, because sometimes, like I think I told you the other day when we're doing some of the homework stuff, like these notes in the class that we take, some of them like I can't like find any ways to answer. Like there's no base to go out to answer some of the homework questions. How come we can't see like an example of some of these conceptual questions in class? That way we have something, okay, here's different numbers, you know, but the same question.
Okay.
See it worked out, and then we can apply that in our homework, and then when it comes to test day, we're like,
Yeah, but
okay.
see, now you're asking for 2 different things.
Okay.
Okay, you started asking for one thing, then you changed. You started saying, show me something like, show me where the concept is, so that I can point to it in the notes. And then you changed the question to show me a question that's just like the one that you're asking, except with different numbers. And that's not going to work. I'm not going to do that. Now, I'd be happy for you to send a message and say something like, hey, I'm looking at this exercise and, well, frankly, I'm not even sure where to begin. I'd be glad to point to you and say, like, well, I think you ought to consider, you know, lecture 7 starting at the 53rd minute. You know, something like that. I'd be happy to say that. But some of the questions really are like, I literally did one just like that in lecture.
Right.
Some of them.
Which I understand that, yeah, but I've been able to go through some of the notes. It's just, there's always like that one question in the homework that I'm like,
Right.
I don't even know where to begin.
Right. But so I get that. I understand that. But I'm not trying to like dishearten you. Rather, you know, send me an email. You know, like you could say, I just can't, you know, I looked through the notes and the video and I don't know, there's something, and then, you know, I can just say, well, literally, I'll just send you a link to YouTube, you know, with a timestamp, and then you can look at it. You know, and if that's enough, that's enough. Then if not, then we can do other things. But some of the questions are just conceptual, and you know, it may be the case that I've covered the concept, and you are familiar with the mechanical stuff, like using the derivative or antiderivative, but you know, I haven't done exactly something like that. But it's at that place where you're going to have to know that, okay, well, this is definitely about slopes of tangent lines, or this is definitely about the area of a shape. So if it's about slopes of tangent lines, this is definitely about derivative. Or if it's about areas of shapes, this is definitely about integration. So I'm going to have to do something like that. And then, you know, and you know, this is a 1,000 level course. If I just left it there and just said, that's all I'm going to give you, then I would think that would be pushing it a little too far, right? Because, you know, I can only, I mean, there's no point in me just like running all of you roughshod, you know, that's not going to work. So, okay, maybe it comes to pass that I give you an exercise as a conceptual one, and you know, it just doesn't happen by the time you turn it in. Okay, well then, look at the key, knock it out on the midterm. And as far as I'm concerned, if you made a flat-out 0 on that, on this one, and then you make a 10 out of 10 on the midterm, terrific, as far as I'm concerned.
Just a crazy question. Is there like a week's calendar? Can I stay on top? Because I haven't been able to find it.
There is. If you look at the announcements on Blackboard,
Okay.
I said something like, here's a calendar that you can click on in a web browser, and here's one that you can subscribe to with your, if you use a calendaring app. There's an announcement for that.
I was looking in the box.
Yeah, so like if you want to do it on your phone, you can like, you know, there's somehow an easy way to do it on your phone, but you can just type that outrageous thing into your phone too.
Okay, thank you.
I get it, okay? I'm not like heartless and you know, like oblivious to the fact that some of these questions are hard. They are, I know that. But I wouldn't be giving them to you if I didn't think you could do it.
And for me, the main thing is just trying to get on the student-teacher linkage, so I know what's going on.
Yeah.
It is very different from any math place I've ever
Sure,
done
yeah.
before, but I've also never done it at a university as a community college.
Right, and different teachers have different strategies, right? Some, you know, my strategy is to push hard and give the students multiple hits to get it, right? So I don't care if you get you know, I wouldn't like it, but I wouldn't care if you get like 1, 2, 0 out of 10, all of the first tries, and then 10s out of 10 on the redos. Okay, well, fine. So, you know, the other reason to do the redo thing, besides allowing, you know, making it to where I can make, you know, have an interesting questions, is that, believe it or not everyone finds the same questions difficult. Some people are going to, some questions are, everyone's going to say, that was a killer. But you know, you do 12 redos, you do 12, you do 12. It's not going to be the same. So then having this kind of policy makes it to where a student can identify exactly where their weak spot was and study in a manner that is most efficient for them, rather than, you know, trying to hypothesize about what might be on the exam and all of that. Yeah?
I was going to ask, could you quickly do this one question that was on one of the Wexes?
No. I won't. And the reason why I won't is because I'm just not going to do that. I don't do that because that's not the structure that's set up. Now, I'll be happy to post a key after the fact and before the midterm. I'll be happy to do that. Other questions?
So is there going to be any kind of review prior to the midterm, or you're just expecting us to use your keys to?
The keys.
Okay.
Yeah. The keys. Because, you know, 30 of them are going to be graded out of 10. And I'm going to post a key for every one of the out of 10 ones. But I'm also going to attempt to do keys for all of the other ones, too. So that's literally going to be like 100 different videos.
Do you have any office hours that you're like, you know, in the office that we can drop on?
I'll be happy to do it by appointment.
Okay.
Yeah, but that's so. So if you'll send me, you know, a message, then we can work something out. Other questions? We'll make it. We'll get through this. Okay, good. Fine. Good. So yeah, stuff like this. You know, I hear this all the time. Like you know, they say, you know, some student. I've even had it. You know, some students in a moment of weakness and honesty say something like, "You know, I paid good money for this engineering student to answer this question." Okay, well, send him my way. You know. So other than that, right? Don't pick up bad slang. All right. So we have this. This is just like we foreshadowed last time. This is the fundamental theorem of calculus. And here's the thing. In this course, well, really year, fundamental theorem of calculus, there are like two big ideas and two really powerful tools, and this is one of them. And this one, by far, is, in a sense, to me anyway, the more beautiful of the two. But it's actually slightly probably less useful than the other one. The other one is the chain rule. The chain rule is sort of like what causes like the world to be like it is. And the fundamental theorem of calculus is sort of like a neat consequence of that allows you to do something surprising. But it's sort of in a real sense, it's, you know, the chain rule is like what's doing the dirty work. Okay, so, all right. Suppose that it is the case that we have the derivative of big F is little f. So that's a statement. Derivative of input function is input function big F is output function little f. So, you know, mechanically it's like, okay, we take a function big F and we put it into the derivative machine, and then out comes another function little f. So the derivative is a function whose input is a function and whose output is a function. Such a kind of function is called an operator. All right. Now, what if you wanted to run the machine in reverse? So, like, the machine is running that way, but what if you know, we mash that, you know, going that way? Then what's that called? Yeah, antiderivative. So we've got antiderivative. The way that we write it is like this. So antiderivative of little f dx is big F of x plus the constant. So now it's, we're running the machine this way. But one of the things I want to impress upon you is that these two things are really exactly the same thing. It's just this one is pointing in one direction, and this is what happens if you turn it around and point in the other direction. And to a very large extent, you can kind of consider it just like this. So if you have, say, like something like this. The square root of y is equal to x. So here's an equation. And if you want to solve for y, that is to say that you want y to stay on its side, and you want x to stay on its side, and you want to do something to this equation so that y is all by itself, then in a sense, what you need is you need the radical to change sides. You need it to leave the y and go to the x. Well, what does the radical do when it changes sides? What does it become? Right, it becomes a square. So, the radical, caterpillar to butterfly, like that, yeah, that's what it does. It changes sides and becomes a square on the other side. And it can go the other way, too. In the same kind of way, you can say, well, what if we have 3y is x, and we want to solve for y. That is to say that we want y like that, and x, so we want y to stay on its side, x to stay on its side, but we want the y to be by itself. So we want to send the 3 to be over, to leave the y. So if it's multiplied by 3 on the left, then what is it on the right? It's divide by 3 on the right. So, that's what it does. And what I'm saying, what I want to, among the things I want to get across to you, is that here's an equation. And if you want to solve for big F, that is to say, you want big F to stay on its side, and you want little f to stay on its side, but you want big F to get by itself. You want to send the derivative to the other side, then what does it get to the other side as? Not quite. It's not really a fraction. What happens when this, just like the radical comes over here and becomes a square, the multiply by 3 comes over here and becomes divide by 3, the derivative comes over here and becomes antiderivative. So, in fact, it's a little bit messy, because the derivative comes over here and splits into two little bits of notation like that. And then, in fact, it can't actually completely go over there because the machine is not entirely and uniquely reversible. So it leaves over this little detritus over here, right, the plus c. It can't entirely make the migration. But derivative and antiderivative are just, it's just like this. Radicals becoming squares. Multiply by 3s becoming divide by 3s. Derivatives, antiderivatives. They're inverse. Mm-hmm. So we've got these two notions, but I want to stress they're the same notion, just one is being read forward and one's being read backwards. Then, besides that, we've also got this notion, which we talked about all day on Tuesday. So now, this notion is antiderivative. This is not antiderivative. What is this? This is integral. Now, they obviously are visually strikingly similar, right? The only difference being the A and the B. Nevertheless, please remember that the definition of integral is you take a shape, you approximate it by rectangles. You use these rectangles to make an estimate for the area, and then you let the number of rectangles become infinite so that you can get a better and better approximation for the area. That's what this represents. This is a representation of saying that shapes, where their areas are concerned, can really be understood as a collection of infinitely many infinitesimal rectangles. That's what this is saying. This one is saying something entirely different. This is saying that this is what the derivative looks like when you go backwards. Okay, they're saying entirely separate things. Also, notice that where this is concerned, the input to the antiderivative is a function and the output is a function. Whereas the input to an integral is a function, and what is the output? A number, right? So the kind of thing that comes out of an integral is a number, not a function. All right. So now, to remind you of the things we talked about on Tuesday, we said that if this is A and this is B, and this is the plot of f of x, then the integral can be obtained like we said. You cut this region into pieces, and then in each piece we select a sample point. So because there's two regions, there needs to be two sample points. So I'll choose like maybe this sample point and that sample point. Notably, the sample points don't need to be like in the middle or any place in particular, but you just have to have some way to somehow choose them. Then from this sample point, you go up to the curve and say, that's how high, that's how high. Then you form some rectangles. Then you find the areas of those rectangles. That is your approximation for the integral using two rectangles, but it's just an estimate. We could get a better estimate by using more rectangles. Okay, so suppose we use more rectangles. Suppose, just because I only like to make the number of rectangles a power of 2. Suppose that it's 4 rectangles. If we're going to approximate this with 4 rectangles, then how many sample points would there be? There'll be 4 sample points, right? Nothing surprising there. So again, like so, blah. Okay, and then the process conceptually, you can continue it for as far as you care to take it. When we get to 4 billion rectangles, there'll be 4 billion sample points. So we will have sampled the function, made little green sampling points 4 billion times in there. And to get to the exact answer, we're going to have to more or less sample at infinitely many points in here, right? So to come up with the value of the integral, you have to sample the inside of this essentially everywhere, right, at infinitely many points. Okay. So the fundamental theorem of calculus, this is all just making sure that we're all clear about the concepts that come before this, right? So derivative, antiderivative, and integral were all defined before this theorem. So here's the fundamental theorem of calculus. If, first, the derivative of big F is little f. Now understand that we have 2 ways to say this. What's another way to say this? Okay, I agree. But I agree that that the prime thing is another way to say derivative. But what I mean is that what would this look like if we move the derivative to the other side? Right. Very good. So i.e. that the antiderivative of little f is big F plus a constant. So these two statements are identical. And 2, if little f is integrable, on the interval a to b. So conceptually, what items 1 and 2 are saying here, they're saying that if little f is a really nice function, if it's really nice in the sense that you know its antiderivative, and furthermore, it's integrable on this interval that you're considering. If it's this really super nice function, then the integral from a to b of f of x dx. Now, that's this, right? This is the one that's saying that in order to carry out this procedure, you're going to have to evaluate little f in the interior at infinitely many points. So this would require infinitely many evaluations of little f in the interior of a to b. That's what the definitions are saying. This is actually equal to the antiderivative evaluated at b, the antiderivative evaluated at a, and subtract them. Now, this one requires infinitely many evaluations of little f, and well, this one is evaluating big F, so it's not even evaluating the same function. But so it's different, at least in that regard. But how many evaluations are occurring here? 2. Wait, wait. Let's write that down. So this is 2 evaluations of big F. And now it's not going to be on the interior of AB, not on the inside, but rather on the boundary. So I want to kind of impress upon you like how jaw-dropping this should seem. This theorem is saying that you mean we're able to exchange infinitely many evaluations of one function on the inside of an interval for exactly 2 evaluations of some related function, but only on the boundary? That's incredible. That is it hardly passes even like even just saying it makes me feel surprised. This is incredible. Okay, so let me try and kind of give a reason why this might seem reasonable. Okay, or let me take a reverse tack and say let me give you a story that is disgusting and doesn't seem reasonable at all. Suppose that you're not well, like you're ill, and you go to the physician and you say, hey doc, I'm not well. I'm not feeling good. And the doctor says, okay, hop on the bed, I'll get out the knife and we'll open you up and see. How about no, doc? Because how about instead of looking on the inside of me, this really invasive and potentially dangerous thing you're suggesting, how about we measure something on the outside first? Why don't you take my temperature? Now, temperature is measuring someone's temperature is a reasonable thing to do. The reason it's reasonable is because, well, what it is that we get infected by bacteria and viruses and things like that, and their metabolism actually is fine-tuned, and so is ours, by the way, to work very near 98.7 degrees Fahrenheit. And if we raise our body temperature, then our metabolism doesn't work quite right, but bacterial and viral metabolism gets completely jacked, like it's just messed up. So our strategy is that we heat ourselves up, and we still more or less work, but the bacteria and the viruses are all messed up. So while they're tripping over themselves, we're killing it. That's the way we work. So measuring someone's temperature is a reasonable estimation. If someone has an elevated temperature, they're probably infected. The reason is because we're all biomechanical machines. We obey rules, that all of us are that way. If I open you up, you're not going to be filled with magic and unicorns. You're going to be filled with meat, human stuff. And if you have a raised temperature, then that is meaningful. That's what this is saying. Because if you have a well-behaved human, then you don't need to cut them open. Just take their temperature, something you can measure on the outside. So from that point of view, that's an entirely sensible thing. That you could make very powerful statements about what's going on inside of something, without even opening it up. That's like one of the fundamental ideas of science, right? Let's not crack that guy's cranium open. Let's use an MRI machine. How about that? Before we get out the knife. All right. So here we go. Good. Let's consider the integral from 1 to 3 of, how about x dx. Okay, and we're going to do this in two ways. The first way we're going to do it is we're going to draw a sketch. Draw a sketch of the shape described by the integral and evaluate the integral using formulas from geometry. And then the second way, I want you to evaluate this using the fundamental theorem of calculus. So we're going to do this in two different ways. And, well, if we've done it right, then we ought to get the same answer both times, right? Okay. So for one, what function are we integrating? Yeah, we're integrating the function f of x is x. So we're integrating f of x is x on what interval? On 1 to 3. All right, so here we go. So that raises the question, what does the plot of f of x equal to x look like? Mm-hmm. It's a line. What's its y-intercept? 0, right? It goes through the origin. It goes through 0, 0. Because if you plug in 0, what comes out? 0. What if you plug in 1? What comes out? 1. What if you plug in 2? 2, right? So f of x equal to x is a line that has slope 1 that passes through the origin. So that's the plot of y is f of x. Then the specific request was to integrate on the interval 1 to 3. Okay? So I drew this so far. What this says, draw a sketch of the shape described by the integral. So where's the shape? 1 to 3? So what should I do? Some vertical lines. Where? At 3? Okay. So here's a vertical line at x is 3. And what else? Anything else? At x is 1. Okay. So what shape is it that we're referring to? This trapezoid. Remember that a quadrilateral where there's a pair, at least a pair of parallel edges is called a trapezoid. So like a square is a trapezoid. So, but this isn't a square because, you know, or a rectangle because these alternate pairs are not parallel. Right. Okay. So we'll get to that. Good. So is there any question about this is the shape that we're talking about? That this integral is referring to. Is there any question about that? The reason why I ask is because this is a conceptual thing, right? Like if you don't have this, look, I wrote the thing. That's my note to myself to post the stuff. Okay. I lost. What was that? Oh yeah. You've got to understand the concept here that integral is related to what with regard to this shape? The area of this shape. So that's the concept you have to have. If you don't have that concept, then I'm going to be able to give you a question that's unintelligible. Okay. So we want the area of this shape. So which, you know, we could, there's a formula for the area of a trapezoid, but just as well we could cut this into two pieces, a rectangle and a triangle, and we could do those formulas. Which one do y'all want to do, trapezoid or cut it into pieces? Do a trapezoid? Okay. So, so the integral is the area of that region. We could do it like this. We could say that it's actually, you know, this, and this would be a perfectly acceptable way to go about doing it. And we could, you know, measure a rectangle and a triangle. That'd be just fine. Or we could. So here's the thing: you've got to know the formula for the area of a trapezoid. So generally, the way it is that you've got two parallel sides, and I'm drawing them. This isn't exactly the shape there. That's a different kind of trapezoid. But there's three measurements that you need for a trapezoid to find its area. You take the two parallel sides and you measure them. So we could call that one H1 and this one H0. Well, 2 I guess would be better. So those are those. And then you need to measure this also. Okay, so then you have to know the lengths of the parallel sides and also the distance between them, W. Then the area is you add these ones together, h1, h2, divide by 2, so the average height, and then you multiply by the width. So that's the area, the average height times the width. Okay, yeah?
Are you gonna go through if we did it the other way?
Yeah, well, I mean, why not? So if we were to do this, then this base would be, well, how wide is that? 2, right? So this would be 2, and how tall is that? 1. Then this is 2 necessarily also, and then you could figure out that this one is 2. Right, so then this one would be, base times height for the rectangle, and then for that one, base times height over 2. You could do it that way. So for our specific case, interpreting it as a trapezoid, whoops. This has height 1, this has height 3, and this has width 2. So, we could, for this one, we could do, in this way, we could say base times height over 2, and then for this one, we could say base times height, and then we could add those together and get a value. Or we could do it with this one, and we could say that we add up the heights and average them, so 1 plus 3 over 2, and then multiply by the width, 2. In either case, what's the answer? 4, right? Because this is 4 over 2 is 2 times 2 is 4. Whereas this is 2 times 2 is 4 over 2 is 2, plus 2 is 4. So in any way you consider it, the area is 4. Okay, using whatever formulas Miss Harris taught you from grade school. Fine. Any question about that? So what that's saying is that therefore we have established that the integral from 1 to 3 of x dx is 4. Because that integral is talking about that shape, and that shape has area 4. That's why. So for part 2, it says to use the fundamental theorem of calculus. All right. So we're doing the integral from 1 to 3 of x dx. Now, this is definitely an integral and not an antiderivative. What is the giveaway that this is an integral? The 1 and the 3, right? Yeah, the a and the b. So then, well, if we squint our eyes, or just hope beyond hope, and consider it to be an antiderivative instead for a moment, and then have a look at this, what we're asking ourselves is that an antiderivative that I know how to do? So, all right, which rule would we use? The power rule. With what exponent? Right, so the exponent would be 1, and so the rule would be x squared over 2. All right, so what the fundamental theorem of calculus is saying is that, well, we're going to take this antiderivative, x squared over 2, and I'm going to continue writing in just a minute, but to remind you, what the fundamental theorem is saying is that instead of evaluating little f at infinitely many interior points, we're actually just going to take the antiderivative and evaluate it at just 2 points, the boundary points, and then we're going to subtract them. So there's a neat notation for that. That is this. So this vertical bar on the right side, and then you write these 1 to 3. In my head, I kind of imagine that the integral here is like moving past it, like, and then it moves past, and as it moves past, it changes shape to this this line. But you know, that's just how it works in my head. What this means is that evaluate the preceding expression at these 2 points, reckon this one as positive and that one as negative, so that it looks like this. 3 squared over 2, because that's that expression when you plug in 3. 1 squared over 2, because that is that expression when you plug in 1. And then what are we supposed to do with these? Subtract them. Now, before we carry out this arithmetic, I claim that you should already know what the end result is going to be. It's going to be 4. Why is it going to be 4? Right, because we already did this in a different way. And if this is right, it's still got to be 4. All right. 9 halves minus 1 half, leaving 8 halves. Which is 4, because obviously it must be. Okay, any questions about this one? Now, so this is an example of the use of the fundamental theorem. Now, here's the thing, is that you can only use the fundamental theorem if you can anti-differentiate the thing in question. If you don't know how to anti-differentiate the thing in question, then you can't use the fundamental theorem, right? If I give you some integral of some crazy thing that you don't know how to anti-differentiate, then no, you're out of luck. All right. To that end, I'd like for you to recall. So recall that the circle of radius r greater than 0, centered at the origin, has equation x squared plus y squared is r squared, and its plot is something like this. Okay. So now I have a question. Suppose that we try to solve for r. Not r. Try to solve for y. All right, so then that is to say we take this equation, x squared plus y squared is r squared, and then I'll make the first move. So if we want to solve for y, surely at least that's going to entail at least doing this. Y squared is r squared minus x squared. Okay, then what? So what do you mean specifically?
You're going to do the inverse, or you want to get rid of the square on the y.
Right?
So
Y equals square root of r squared minus x squared.
Okay. Y is square root of r squared minus x squared. This is not right. But it's the most common incorrect answer. So don't feel bad. But it's not right. So here's the thing. I take it to mean that you did something like this, that you wanted this square to travel over here, and as it traveled, it became a radical. And I'm saying that that's not permitted.
You have to divide everything by y.
No, that won't work either. which you may be saying, no, wait a second, I'm sure he wrote that on the previous page. Let's call him on it. Okay. So notice what I did on this page. What did I do? I changed a radical into a square. That's what I did. And what y'all are suggesting is not the same. You're suggesting changing this square into a radical.
I thought you said that you could turn the square, that you could go backwards.
Can you? Okay, so let's think. Suppose that we take a 3 and we give it to the squaring machine. Then what comes out? 9. And then we give it to the square root machine. And what comes out? A 3. So this particular example would lend credence to your belief that that you can that one can undo the other.
There's two different, so we're talking about two different things.
Okay, so what about this one? What if we give input -4 to the square, the squaring machine? What comes out? 16. And then we wire that up as the input to the square root machine. What comes out? So the fact that something different is coming out than what was input is telling you that, no, in fact, you can't quite undo it. So what I'm telling you is that the machine works the way you expect, this way, but not that way. So, to be clear, what's happening here is that what you meant is that if we take this equation and then we compute square roots of both sides, it's fine. This is still correct now. But the question finally is, what is the square root of y squared? The answer is not y. It's not that either, because only one thing is allowed to come out of the machine, right? The machine doesn't have two outputs. The answer is the thing that many college algebra students forget, and then many calculus students forget. It's not this, it's this. The absolute value of y. Square root of y squared is the absolute value of y. -4 went in, +4 came out. That's the absolute value. So, that's why I said try to solve for y, because in fact, you cannot. You cannot solve for y in this equation. It is not possible to do it. Not possible to do it and maintain a single equation. Rather, what you can do, what is possible, is that you can split the circle into top and bottom halves. The top half is this. But just the top half. So when y'all said, this one becomes that one, in a sense, it was like you were saying, this red picture is the same as that one. Like you just forget the other part. So then what is this one? This is y is equal to the negation. Okay, so the top half of the circle is given by the red formula and the bottom half by the green formula. All right. With that context now, and to remind you of those things, I could ask, what is the integral from 0 to 5 of the square root 25 minus x squared dx. And so here's the thing, is that, well, you've got this shiny new tool, the fundamental theorem, and you're itching to use it. So it comes down, you know, if we're going to use the fundamental theorem, we have to ask, can we do the following antiderivative? Antiderivative. Can we do the antiderivative square root 25 minus x squared dx? Okay, now. A substitution? Okay. So let's try it out. So you're telling me that I should do the variable substitution u is equal to what? Okay. 25 minus x squared. Now, part of the, you know, what is it? The beginning of knowledge is the rectification of names, right? To know the true name of something. So this substitution, what's the true name of this? Well, it's really the anti-chain rule. But that one, right? The variable differential substitution. So what's on offer is that we're saying we're going to substitute these variables, but the process cannot be completed until you explain how you're going to substitute differentials. So if variables are going to be substituted like this, how do we figure out how differentials must be substituted? Which is to say, if u is going to be this, what's du? Right? So we calculate du dx is negative 2x, and then du is negative 2 times x times dx. And then I won't ask, I'll just move the negative 2 to the other side, because that's what we always do with the constants, more or less. And then I'll do this. And now I'll say, well, is it going to work or is it not? It's not going to work. It's not going to work because, well, we have a dx, that's good. I can get the negative 2 out of the way by doing that, that's good. But this x, what's going to come of that? There's nothing we can do, really. So, all right. Also, remember that one of the heuristics of doing the substitution is that you want to be on the lookout for a pair of polynomials that are somehow being more or less multiplied or divided, and what must be true about their degrees. Not the same, but they have to differ by 1. So that means that if we're doing a variable differential substitution with involving a polynomial of degree 2, then there needs to be a polynomial of degree 1 hanging out somewhere. Now, is there a polynomial of degree 1 hanging out anywhere? There isn't, right? That's the polynomial of degree 1 that we need, but it's nowhere to be found. So we can't do a substitution. So to move the question forward, I'll just tell you that it is in fact possible to anti-differentiate this, but not using anything that you're going to learn in this class. So, you know, I'm just remarking that there's other things out there in the world, but they're not accessible to us in here. So we have no idea how to anti-differentiate this in here, but there do exist ways. In fact, we don't know how. For those of you that just want to look stuff up, you know, and don't want to be, you know, can't stomach that I'm hiding something from you or whatever, the way that you would do this is using something called a trigonometric substitution. But we don't do any trigonometry in this class, so then it's just like off the table. All right.
Is that pretty difficult?
Well, I mean, I don't know, it's a thing. You know, I don't know. It's you know, we talk about it a lot in the 2000 level calculus courses. But you have to know trigonometry to be able to make your way through it, which is not a requirement for this course. Okay, so then is that it? I mean, do we just say give up? Yeah, right? Because well, what are we asking about here? Right? I didn't say like use the fundamental theorem of calculus. All I said was evaluate this integral. I don't really. You can use any legitimate method that you want. Well, what this is asking about, this is saying that we want the area under y is equal to the square root of 25 minus x squared on the interval 0 to 5. That's what's being asked for. Well, what does y equal to the square root of 25 minus x squared look like? What does that look like? That's a circle. Which half? The top half. This is the top half of a circle that's centered at the origin. What's its radius? 5. Because remember, this number is the radius squared. If you look on the previous page, that's r squared. So 25 is 5 squared, so this is a circle of radius 5. So so this is y is the square root of 25 minus x squared. Okay, so that means that what is this? What is this? X value? -5. And this one? 5. Good. So now, concerning this picture, this sketch we've just made, what does this sketch have to do with the integral? What area? What do you mean? 0 to 5, right? So now, what I'm saying is that when I get to this point, a lot of students sort of bite hard, and they think, it's all of this area. But it's not all of this area. What is it actually? 0 to 5, right? It's just the stuff from 0 to 5. So that's 1/4 of the area of the circle of radius 5. Therefore, we can answer the question. The integral from 0 to 5 of the square root of 25 minus x squared dx is, well, pi r squared would be the area of the whole circle. That's the whole thing. So how do I get the answer? Right. So that's the answer to this question. So now the purpose of me going through this is, to remind you of some things about algebra, and also to hit the concept very hard about what integral is. And also to, the concept being that integral is an area. And furthermore, to circumscribe the usefulness of the fundamental theorem. The fundamental theorem is circumscribed very hard by it's only usable when you can anti-differentiate something. If I give you something that cannot be anti-differentiated, then you can't use the fundamental theorem, at least not directly. But there may be other means. Any question about this? so there's two different questions there. So, so there's a couple different questions there. If you mean that it is not possible using the knowledge that you have, or it's just like cosmically not possible to compute the antiderivative, then that's one, like the previous example. Then needs be, you must have some way, right? So then, if I give you something that can't be anti-differentiated, and also there's no other way to do it, then I've made an error, right? I've given you a bad question. If that's what you were wondering. But it could come to pass that you think that it can't be anti-differentiated, but it really can. Or it might come to pass that it can't be anti-differentiated, and you can't imagine any other way to get at it, but in fact there is a way. That could happen. Okay, so let's have another one. So how about, let's do something nice and easy now. How about integral from 1 to 4 of 4t cubed dt? And again, no, what am I trying to say? No further instruction is given. Just do it in, whatever legitimate way you can think of. So, well, can you use the fundamental theorem? Yeah. Because, well, it's definitely an integral because it has the limits 1 to 4. But if we obscure those for a moment and ask ourselves, would I be able to do that antiderivative? The answer is, yeah, I could do it. I could do it. So what is the antiderivative of 4t cubed dt? T to exponent 4. So now, I want to point something out. And that is that the first time I used the fundamental theorem, 2 exercises ago now, right there, notice that, I calculated an antiderivative, but I didn't write the plus c, right? And this is after us doing antiderivatives and me saying plus c, plus c, plus c, really harping on that. And then I don't write it here. Okay. Well, here's the fact, is that when you're using the fundamental theorem, you can use any antiderivative that you wish, any one of them. So then me not writing the plus c is making the conscious choice that I'm going to choose the one where the c is 0, because that makes my life easier. But just to convince you that it really cannot matter which one you choose, just to make a point, I'm going to do t to 4 plus c, and then evaluate it from 1 to 4. Right? I'm going to put the plus c in there. Okay. All right, so I'm going to evaluate this at 2 places, at 4 and 1. So then this will be 4 to exponent 4, and then plus c. But wait a minute. Wait, let's see. If I write it like that, and I do 1 to 4, and then plus c like that, then why didn't I plug in 4 for the c? Right. The 4's get plugged into which symbols? The t's, right? They're just not to, the answer is as simple as, well, that's not a t. Okay, so now that I did it, what's going to become of the c's? They just cancel, right? Plus c, minus c. They just go away. If I had written plus pi, the pi's would have canceled. If I had written plus 1326, the 1326s would have canceled. All right. 4 to exponent 4 is, what, 256? Yeah? And then minus 1. So this will be well, I'll write it like this, 256 minus 1. So then the answer would be 255. I'd like to point out like how startlingly straightforward this is. Like I did it on basically a single line. If I hadn't have done the plus C bit, it literally would have fit on a single line. We didn't draw a sketch. We didn't cut stuff into rectangles. We didn't compute a limit. Just blammo, right? Fundamental theorem, yeah?
Do we always have to put the plus the C's, or can we just?
Please don't.
Okay.
I mean, feel free to. You can write,
Since it's always going to cancel.
right, you can write plus whatever is your favorite number, you know. But the fundamental theorem is saying that you can use any antiderivative. So by not writing the C, conceptually that's saying, oh, I'm choosing the antiderivative where the C is 0, so that I don't even have to write it. Okay, good. Any question about this one? All right. Good. So how about the following remark? So when we talked about the derivative, or well, when we reviewed it anyway, because you all talked about the derivative in Calculus 1, one of the things is that the derivative is homogeneous, which means that constant multipliers can be factored in and out. All right. In the end, the reason why the derivative is homogeneous is because it inherits its homogeneity from the limit, because a derivative is defined in terms of a limit, and the limit procedure is itself homogeneous, and the derivative inherits its homogeneity from there. The antiderivative, because it is the same thing as derivative but in the opposite direction, is itself homogeneous. Finally, if you recall, integral is defined in terms of limits of Riemann sums. So integrals are also defined in terms of limits. And because of the way things are arranged in there, the homogeneity of limits is bestowed also upon integrals. So integrals are also homogeneous. Okay, good. It would be surprising if they weren't. So what I'm saying is that if you integrate from a to b, and you have some constant k and a function f of x, and you're integrating with respect to dx like this, where k is a constant, then this is saying take your constant, take your function, multiply them together, and after you've done that, integrate. This rule is saying that, in fact, it would be acceptable for you to integrate your function first and arrive at the answer, and then only after that multiply by your constant. So these are the same thing. Constants can come in and out, just like antiderivatives and derivatives. Any question about this one? 2. The derivative is additive, and so is the antiderivative, and also the integral. What I mean to say is that if we have two different functions, this is saying that you take your two functions, you add them, and after you've done that, integrate the result. This rule is saying that, in fact, it's just fine for you to integrate the functions individually. We'll integrate each one. And then after you've integrated each one, then add them. Add the results. So you can do it like that. Beautiful. There's a tiny little thing here that doesn't really come up in our class, but as a mathematician I have to say it, and this is assuming f and g are both integrable. You can more or less just dismiss that comment as just noise that the mathematician has to say so he can sleep tonight. Okay, okay, good. So now I'm going to write something that kind of looks like a righto by analogy to a typo, but it's not. And so I want you to point out what weirdness is going on here. So I suspect it kind of looks like I made a mistake writing something. But I've done it on purpose. What weirdness is happening here? Yeah, it's saying the integral from a to a. From a thing to the same thing.
Zero,
It's going to have to be 0. Why?
because 5 minus 5 is 0.
There's no space.
There's no balance, so it goes to itself, which is.
Well, let's look at the picture carefully. Y'all are right on top of the reason. Let me just draw you a picture so that we can, all put it into words. So here we have this point A. And here's the function f of x. What does this integral have to do with that picture?
Finding the distance of A, if you're not going anywhere, it's 0.
Okay, we're right on top of it, but I can't check off the conceptual an area. So we're asking, in a sense, how much area is under the curve and above that single point? 0, right? You can imagine this as being like a trivialized rectangle that has height f of a, but base 0. If you had a rectangle, with such one of the dimensions is trivial, then what's f of a times 0? 0. So there's a 0 area above a point. Now, the way this comes up in this class and in other places is that I do something, I'll write something that's just like obnoxious, like this. Something crazy, like there is no antiderivative of this thing, like ever. This is not the kind of thing that's possible to do. And then write something like this. And then students will stare at it for more than the 3 seconds that is necessary to understand the answer. So what's the answer? 0.
How can it be 0 if you can't even get the antiderivative?
Because the question is how much area could be under this curve above that single point?
But is that a curve that can be plotted?
Sure.
Okay.
Yeah, it can be plotted.
I just can't get the
You can't anti-differentiate it. So, I mean, part of the, okay. So then, part of my job is to teach y'all to do, for this course. But another part of my job is I've got to, help with the training of graduate students. And one of the, fun things that instructors do with fresh young graduate students is we give them something like this and say, do it. And what happens is that very often is they just like get into a cold sweat. You can see they're like panicked, like panicked. Because what happens is that if their education, now these are math majors, if their education hasn't firmly circumscribed the usefulness of the fundamental theorem, then what happens is that instead of observing that this is an integral, what they see is this, and they think, I have no idea how to anti-differentiate that. I don't even think that can be anti-differentiated. Should I tell this guy? Should I tell him that it can't be anti-differentiated? Maybe it can. Maybe I don't remember right. They get like in a cold sweat. I can see them like getting all worked up, and I let them get worked up for a good 1 or 2 minutes, and then I ask them like, what are the limits? And then 0. Okay. So I'm telling you this because don't let that be you. Okay? There's no need, if I put this on a timed exercise, there's no need to spend more than 5 seconds on it. Okay? But I promise that I'm not the only instructor who does that, and to graduate students, and it's going to go on forever. So that we can, break them of that habit. All right. 4. Here's another one. Now this one also is kind of high concept. So this is what I mean. Like, this is a conceptual question. Okay. Here's another one. Now, remember that the geometric interpretation of integral is area. All right. So in particular, it's all that all that area there. So now, well, here's one of the things about area is you can cut the area into 2 pieces, and that doesn't modify the value of the area. So what if, you know, we cut it like right here at C, say. And what if it's possible, so now there's 2 regions. What if it's possible for us to compute that one, and it's also possible for us to compute that one? Then how could we get the whole thing? By adding them up, right? So what I'm saying is that, you know, if there's like some scissor right here, it's my artist's impressions of scissors, then we can say that, oh, well, what would this one be? What integral corresponds to the left region? A to C. F of x dx. And then the right region? So you got to go in the same way, right? So because this one is A to B, that means that this one needs to be A to C and C to B, right? And then, so we calculate them separately, and then do what? Add them up.
If we see that we would have to do the extra work, we could just, you know, we could go from A to B, right?
Well, yes, but I'm going to give you situations where you can do this one, where going this way is easy, and I'm going to give you, is you know, more or less that going this way is the only way, and I'll give you other ones where going this way is the only way. But you know, and understand that if you can cut it into 2 pieces, then you could just as well cut it into 3 or 300. But it's never going to be that many, because that wouldn't be gradable as an exercise. All right. Finally, the integral a to b of f of x dx. So now I'm gonna write something, and it's not completely correct. So if you copy it down, be sure to copy down the edit that I make. Okay, so this is not right, not yet. What's the difference between the left and right hand sides at the present time? The b's and the a's are switched, right? So all right. So now the question is how do we need to modify this so that it is correct? All right. So let's go through a thought experiment for a moment. Yeah?
It's not absolute.
Not quite. There's something there though. Let's go through the thought experiment. Back to Walmart, and we've got a security camera on a register. And suppose that we watch like an hour of footage. And from the footage, we are able to determine that the amount of money in the register has increased by $1,326. Right? Just because, you know, this is not a credit card one, this is cash only. So we're able to like physically see it going in. $1,326. Now, you know, suppose we give this to our alien friends who are not so familiar with the way things work on Earth. And they watch the video, but unbeknownst to them, they're actually watching it in reverse. You know, instead of watching it from 7 p.m. to 8 p.m., they're actually watching it from 8 p.m. to 7 p.m. Then, as far as they're concerned, what would be true about the money? Yeah, it would be that that register, you know, has made
So it's negative.
negative $1,326 because the flow of money has been reversed. So instead of making positive money, that register is making negative money. So what I'm telling you is that the switching of the limits conceptually corresponds to that reversal, and yes, to make it right is a negation. Now, that's a fine way to think about it. You know, I try and, you know, give you all stuff like that to think about. But I will say that in my mind, that is not even close to the way it works. Rather, in my head, the way it works is that in the first case, when we're doing it like that, if A is less than B, that means that dx is a positively oriented element, followed up by f of x, which is another positively oriented element, and this causes the rectangle to have a counterclockwise swirl, which is reckoned as positive. Whereas if you do it the other way, going from B to A, so now you're going, you have a negatively oriented dx, and then follow that up by a positively oriented f of x, then that causes the swirl of that rectangle to be clockwise instead of counterclockwise, and this is the positive orientation of the space, and this is the negative orientation of the space. So I'm just letting you know that you know, there's really nothing to do with money here, but I'm also sort of exhibiting my bias in that my mathematician's bias, in that everything I construe is geometric. But whatever. You don't need to know this. I'm just telling you that you know, this can be considered in a purely abstract way. Any questions about these? All right. So now you asked about this. So now I'll give you one. Let's consider the following. How about I say let f of x be the following. Let it be, how about 3x squared plus 1 when x is less or equal to 2. Let it be, how about 3? No, not 3, 4. When 2 is less than x is less or equal 5. And how about 6 times x minus 7 when x is greater than 5. So this is a piecewise defined function. In a sense, you know, you can look at each one of these, and if you considered y equal to the first expression, that thing would be like a parabola. Y equal just that. And y equal just that would be a horizontal function, right? A horizontal line. And if it was y just equal that, that would be a line of slope 6. So what you can kind of imagine that what this function is a function that kind of, you know, isn't entirely sure what it wants to be. Right? Some of the time it's like this parabola. Some of the time it's this horizontal thing, and some of the times it's this slope thing. All right? So this is a piecewise defined function, and each one of these pieces, the name for them is clauses, and they're numbered 1, 2, and 3. And if it was a fall semester instead of a summer semester, I promise you I'd try to get in a Santa Claus joke. But it's summer, so I'll just omit it. So the way this goes is that, you know, at input 2, this function changes its mind from being a parabola to a horizontal function. So it's like, I'm going to be a parabola to the left of 2, but then to the right of 2, at least immediately to the right of 2, I'm going to be this horizontal function. All right? So at 2, it, you know, we'll need to use the first clause to evaluate the function, and it'll be a parabola, and it'll look like this-ish. So should I draw that dot? That dot right there, should it be solid or open? Should be solid. What makes you say solid? Less or equal. Okay, good. All right, good. So then from there, it's going to be this horizontal function for a little bit. It's going to be like this. But it's not going to be that horizontal function forever. It's only going to be that horizontal function for a little bit. Where does it change its mind next? At 5. So this is at x is 2, and this is at x is 5. So at x is 5, you know, it's being the horizontal function. And then again, this is solid because it says less or equal 5. All right. Then, beyond 5, then it wants to be the sloped function. All right. So then it'll be like this. And it'll be evaluated using the third clause. So that's what this function does. Okay? So is everybody okay with that? This is just a rough sketch. Now here's the question. Please evaluate the integral from 0 to 7 of f of x dx. Well, all right. What is the geometric interpretation of integral, by the way? What is it related to? Fishing for the A word. Area. Okay, good. So then, what area are we talking about specifically? It surely has something to do with this picture. 0 to 7. Okay. So if I mark out x is 0 here, like this, so if that's 0, and 7 here, like this, then what specifically are we talking about? Right. This much, right? So this much, and also this much, and also this much. So that's what we're talking about. All right. So, well, as for this piece, we could just use formulas from Miss Harris's class, right? And that piece too, because that's a rectangle and that's a trapezoid. So we'd be fine there. But then for that piece, you know, we'd have to do something else, probably the fundamental theorem. But let's think here for a minute. Can we just like use the fundamental theorem directly? The question is can we anti-differentiate f of x? Right, because how many antiderivatives do we know? 3, right? We know 3 of them. We know the power rule, the log rule, and the exponential rule. Now, of those 3, how many of them have piecewise defined functions in them? None of them, right? So can you use the fundamental theorem right now? No, you cannot. But we just got finished saying that, in fact, we noted that you can take shapes and cut them into pieces, and that doesn't affect their area. Which means that if we could somehow conveniently and cleverly cut this shape into some more convenient pieces, that'd be just fine as far as the integration is concerned. Well, I would go so far as to say that cutting this at x equal to 2 might be a pretty good idea. So what I'm saying is that, you know, we could do it like this. We could say that this is the integral from 0 to 2 of f of x dx plus the integral from 2 to 7 of f of x dx. You know, just saying that cutting it there between the transition, you know, from clause 1 to clause 2, from the red to the green, that's a nice place to cut it. But it does work. Why wouldn't it?
It changes the 5, so wouldn't we need to go from 5 to 7?
Ah, good. Because, well, if it's permissible to cut into 2 pieces, then I can cut one of the remaining pieces into 2 pieces as well, right? So yes, I agree entirely. Let's also cut at 5. And now here's where the last bit needs to, the last insight before we can, you know, get to the boring part. So right now what I'm saying is that we're in the midst of the conceptual part. Okay? We're about to get to the part where it's just, okay, I'm going to turn the crank so that we can just apply all the formulas that we know. So here's the thing, is that that function right there, that is not in the table of antiderivatives that we know, right? The table of antiderivatives that we know do not include any piecewise defined functions. But consider this f for a moment. And note that this integral is asking exactly and only between 0 and 2. Well, yes. Now, that means that because we're integrating between 0 and 2, again, you can imagine yourself being really, really little. If you're right there, as far as you're concerned, the whole world is that red world, right? If you're, you know, infinitesimal, who knows what's going on over there? As far as you're concerned, that's the whole world right there. So for this integral between 0 and 2, what can we replace f of x with? 3x squared plus 1. Similarly, for the between 2 and 5 world, what can we replace f of x with? 4. And for the between 5 and 7 world, what can we replace it with? 6x minus 7. So now, could we use the fundamental theorem right here at this position? We could not. But I'd like for you to observe that through some conceptual considerations, we have changed the integral, this one integral, for which it would not have been possible to use the fundamental theorem, and we exchanged it for 3 integrals. And we can use the fundamental theorem on each piece. Right? So, does that answer your question? So, you know, we can just do it. So I'm just going to like rush through this because this is the boring part now. So can we agree that the fundamental theorem can be done on each one of these? Okay. So then, you know, we compute the antiderivative. That'd be x cubed plus x, evaluated from 0 to 2. And then plus, what's the antiderivative of 4? 4, good, 4x plus c. So notably, well, the most common wrong answer to what is the antiderivative of 4 is 0. That's the most common wrong answer. You know, and I suppose my theory, my working theory for what that is that student did derivative instead of antiderivative. Okay, then plus, for this one, this would be 3x squared minus 7x. And then evaluated from 5 to 7. Okay, then fine. So then this would be, boring. So this would be 2 cubed plus 2 minus 0 cubed plus 0 plus 4 times 5 minus 4 times 2 plus 3 times 7 squared minus 7 times 7 minus 3 times 5 squared minus 7 times 5. And this is calculator work, okay? This is boring. As far as I'm concerned, this is why, the concept is what humans are good at. Right? We're not any good at this arithmetic stuff. That's why we made calculators. So, this is where the calculator takes over. But any question about this? So you need to, come to some final response to get full credit. But the thing is that getting to, supposing an exercise just like this was graded out of 10, getting to this place is like 9 out of 10 points. Having the correct arithmetic, navigating this arithmetic jungle is worth like 1 out of 10 points. Okay, it's all of this stuff that led up to it that is the effort that is graded. Any question about this? Okay, so now, one thing has been absent entirely from our considerations, and that is that 2 lectures ago, we talked about, 2 lectures ago, we talked about substitution. Notably, we haven't done any fundamental theorem exercises that require substitution. So, now, my intention here is for you to get a very strong echo of, wait a second, didn't we do that one earlier? Yeah, it's very similar to the one that we did earlier, right? The difference being that earlier we didn't have that x, right? And we mentioned that in fact we can't use the fundamental theorem because in this class we don't know how to do a trigonometric substitution. Nevertheless, we could still answer the question by relating this thing to the top half of a circle. But here we have the x. Okay. So what are we going to do? What do you mean split them up? Oh, no. I got to write down what you said, though. So you said do it like this. Okay. So for any of y'all copying this down, you have to copy down that it's not right. Okay. So this won't work. It won't work for a variety of reasons. One sort of straightforward reason is that what if I wanted you to differentiate that thing? If I wanted you to differentiate that product, then you'd have to use the product rule, right? And does the product rule say derivative of the one multiplied by the derivative of the other? It doesn't, right? It does something more interesting than that. It says derivative of the first one multiplied by the second plus the first one multiplied by the derivative of the second one. So the derivative does something interesting with products. And as a result, so does the antiderivative and also the integral. And it is not this. It's not what it does. So rather, we're going to do the substitution. So we'll say u is 25 minus x squared. Du dx is negative 2x dx. No, not dx, because I left the dx on the left side. So then du is negative 2 x dx like so. And then du over negative 2 is x dx. So now, there's a twist, something new that I need to illustrate. So I'm going to take this integral. I'm going to copy it down here to help us keep track. So in the first place, I'm going to commute these two because multiplication commutes. So I'm going to write it like this. 25 minus x squared, and then multiply by x dx. So I'm just doing that so it looks nice. So that this red corresponds to this red, and this green corresponds to this green. But here's the thing. We're not doing an antiderivative. We're doing an integral, right? So when I copied this from here to here, I didn't copy the limits. So I'm going to copy the limits. But now, here's the thing. This is from 0 to 5. But what variable is between 0 and 5? X is between 0 and 5. So this is really between x is 0 and x is 5. Now here's the thing. This is a variable differential substitution, which means that all variables and differentials and all other quantities for that matter that are in terms of x, we're changing them to be in terms of u. So what I'm telling you is that this expression in terms of x is being turned into that u thing. This differential expression in terms of x is being turned into this differential with respect to u thing. But we have not yet said what's going to occur to these limits that are for x's. If we're going to change things to u's, we need to say how the limits are to be interpreted as u's. So we need to change the limits. Okay, so the question is the first question is what are the limits? You know, that's what we need to ask for ourselves. So u evaluated at 0. So what is u evaluated at 0? That is to say, take this and plug in x is 0. It'll be 25, because it'll be 25 minus 0 squared, which is 25. And u evaluated at 5 is what? It'll be 0, because it'll be 25 minus 5 squared, which is 0. So what I'm telling you is that this now is replacing that. So that's the new bit. Okay. So now let's write down the new thing here. So this will be integral square root u du over negative 2. Okay, but what are the new limits? Okay, so is it 0 to 25? 25 to 0. Why is it going to be 25 to 0? What are we replacing the 0 with? The 0 becomes a 25. What are we replacing the 5 with? A 0. So normally, you know, once you get comfortable, you stop writing the u equal thingy so that it looks like this. Now, admittedly, you might feel a little bit disturbed, like saying, okay, those are not in the order that I want, and I'm feeling uncomfortable. Okay, no dispute. So if I factor out the negative half, like that, then in one more step, we can get those limits in the order that we want. That is to say that, you know, you probably want them to be in the order 0 to 25, like this. But what's the cost of doing that? What's the cost of flipping the limit, the order of the limits?
Negative.
A negation. So this negative half
Turns into 1.
turns into half. And then this is a question that you could have done half an hour ago. So we're going to have to leave it there because it's time for a quiz. Okay, so any question about this? So you'd have to finish this. So you finish. And this step is because the integral from a to b of f of t dt is the negation of b to a of f of t dt. Any questions? Okay.
Substitute the u's back for the original expression. And
No.
then leave it like that.
Yes.
Okay.
The reason is because what kind of, well, in the first,
Substituted the bounds of the.
right. So, well, and yes, the thing is that, is this an integral or an antiderivative? It's an integral. What kind of thing is the output of the, a number, right? So whatever number it is that you arrive at, that's the answer. There's no need to go back.
Is there a difference in the output if you had left the bounds, the original one, and then substituted the x expression back in?
If I understand what you're saying, then the answer will be no.
Okay.
But as long as you're doing what I think you're saying.
Yeah.
Okay, but we'll talk more about that next time.